is an adaptation of some older update rules, that is fair to say. And the algorithm is very simple to implement. On the forward pass, we run the solver, yay. On the backward pass, we compute this W prime, this modified instance, and this is based on the incoming gradient. We run the solver on the modified instance, and we have this simple formula for before. What is the main technical contribution, I would say, is actually the theoretical part. We have seen implementations of this rule in some few years old, a little bit obscure papers that were again motivated by this lambda going to zero theorem. And there were amazing sentences that I really enjoyed reading. Well, the theory says that lambda should be close to 0, but we in fact found out that 1.0 works better than 0.1, so we used it. And, I mean, good, but no. So what we did, the main technical contribution, is really justifying in theoretical terms how every value of lambda makes sense. It's a true hyperparameter. It does not want to be small. We have seen cases when it's 1,000. It really depends on what is the scale of the weights coming in, what is the scale of the loss function, and so on and so on.
Lambda fixed or the training or it's evolving?
That's a great question. I mean, it depends what you want. You can do whatever. And we got this question a lot. So eventually, we really tried all sorts of schedule and all of that. And in fact, a reasonably tuned constant lambda works as well as anything. So in our ongoing works, we never needed these schedules. There might be something to win on some maybe harder problems. I don't know, but we have not needed it yet for us. Up until now, it was a constant. And then behind the scenes, there is some discrete geometry happening. So what our mathematics talks about is exact description of these piecewise linear interpolations. This is the object that we give guarantees about and how these interpolations depend on lambda. And maybe I'll skip through this, but there is some interesting mathematics in terms of how these different linear pairs arise and how they are connected to the original function. And this is exactly the language of the theoretical guarantees that we used. Behind the scenes, and this is not expected to be read, just to catch a few words, you see that we talk about hyperplanes and half spaces and polytopes and objects from discrete geometry, which it's in some way this had to happen. The core technical language had to be somewhere between discrete mathematics and continuous mathematics, because we still want to talk about gradients, but we have this discrete pairs of constant values. So this is exotic in terms of optimization arguments. You do not usually see discrete geometry in an optimization paper, but that's what it was, and that's also some part of the paper that we enjoyed. That it's like somewhat different than what you usually see. But again, this is not expected to be read at this point. I mean, enjoyed in the paper if you like these things. The real question was, okay, we have this update rule. We can plug in the solvers. What is it going to do? Is it going to train at all? Is it going to be awful? Is it going to be too slow? And we wanted to find out. First of all, for the ICLR paper, for the first one that had all the theory, we just wanted to see on synthetic problems, on problems that we created ourselves, that all had the spirit of combinatorial problems on raw images, on raw inputs. And we did 3 experiments in the first paper. We used off-the-shelf solvers. We coded up Dijkstra's algorithm, or we used integer programming, commercial solver. We tried to have respectable instance sizes to really see that, to enjoy the fact that we're not making sacrifices on the combinatorial side. So we try to scale up the instance sizes, and we also try to scale up the input images just to show that, okay, the architecture can deal with sort of ImageNet-sized images, and it is applicable in general. I'll describe one of these problems. We had a lot of fun generating synthetic Warcraft 2 maps. And what's going on here, the input is this map that consists of the Warcraft 2 tiles. And is the shortest path from top left to bottom right under some terrain costs. Water is more expensive than grass, and so on and so on. And the data set does not explicitly contain these terrain costs. It only has this input map and output path. This is the data set, and the unknown terrain cost is something to be inferred by the network. So obviously, we would like to have this architecture that first takes a ResNet. The ResNet spits out some representation that goes into the shortest path solver, into the Express algorithm that spits out the path. We compare it to the ground truth path and train end to end. And we had similar such problems for the perfect matching and for the traveling salesman. What we saw was nice. We were happy that the standard architecture, the baseline, there was a pure ResNet from the image straight to the shortest path. It was able to memorize every training point. We had 10,000 training maps, but the generalization was awful to non-existent on the bigger map sizes. Whereas the architecture that we had, that had the ResNet and then the solver, once it managed to learn all the training examples, it actually learned the correct representation, the correct hidden costs, and then it had near perfect generalization. I mean, this is a synthetic example. I do not want to overstate it. We all know how these work, but it was a good sign. Maybe even more importantly, the training of the architecture felt like any other deep learning training. We did not feel any specific pain related to having the solver in there. The constant lambda was very easy to tune, and we may have had problems saying the traveling salesman that we needed to do some regularization and so on, but these were standard deep learning problems. It did not feel that we are in some new exotic architecture that requires all different types of attention and so on. And that was maybe the best sign that we had from these experiments. And we were encouraged to see, okay, the idea was always to apply it on actual benchmarks to show that it can work. So eventually we needed to move away from synthetic problems. And we came back to, at some point, we came back to this matching problem. And this matching problem, the setup is that you get a pair of images, and you also get the key point locations on the input, and you're supposed to provide matching of the key points. And this benchmark this comes from the line of work I mentioned earlier, and it is really designed to test these deep graph matching solvers. So it is designed so that you do not see too many training examples. So you really need to have good generalization, and the examples are, in some say, combinatorially interesting. There is lots of conflicting evidence. There are changes in orientation. If you see the chair example, that is quite nasty. Every leg of the chair looks the same, and you need to understand the geometry. There are non-rigid objects that face you from different orientation, like the sheet. And some parts are even hard for humans. If you look at the train example, the one bottom right, then getting correctly which is the correct light in the front, they are next to each other, then some are even hard for humans. So this is how the dataset is designed.
Okay. Mm-hmm. So this is you're looking for permutation?
Yes.
So no outliers on either side, we're looking for permutation?
Yes and no. So the original setup was looking for a permutation. And since we had an arbitrary solver in there, we proposed some new benchmarks where you have arbitrary number of outliers on both sides, because we were not happy with the setup where it's just a permutation. But the benchmark, as it was laid down for us, only was looking for a permutation. I agree, it's a lot more interesting with outliers, but there's also a point that we were able to make that we can.
I'm not denying that. I just wanted to know exactly what we are now.
Yes, correct. I mean, so in the main setup of the paper, it's a permutation. And so then I would be curious to have some conversations, because I know that there are people here who work on image matching, where the setup is a little different. There are more key points, maybe more rigid objects, and so on and so on. But maybe there is something we could do. So what we did, we want to say, okay, we can use these best graph matching solvers. So we sat on a train and went to Heidelberg, where there are strong computer vision groups who write these solvers, and we came back with these amazing implementations. We wrapped them, and we built an architecture around them. And this is a complicated sketch of a simple thing. Effectively, at every key point, we extract the VGG features, and we also get some more global features from the images, and then we simply construct these unary and binary costs of the graph matching problems. So how each vertex in the graph is similar to each vertex, and how each edge in the two graphs is similar to each edge. We take the constructed instance, run it through the Blackbox solver. We have the loss function because the supervision is really the ground truth matchings, and we train it end to end.
So I have a question. Now, in this approach, you are constrained to have the final loss function based on the graph. So for instance, if you have two bikes which are flat, maybe there should exist some homomorphy that maps all the points to each other. In your approach, you are restricted to have the loss function in this particular case defined on the graph.
I'm still not sure I understand the question.
So if you have a flat object, there exists a mapping, simple mapping with 8 parameters that has to map all the points one to the other. So if there was no deformation and things like that, but there could be some global constraints. But in your case, you are modeling the loss on the graph only.
Yes, I think that is correct. I would say that this is an artifact of the benchmark and not of the black box, of the incorporation of the solver, because the solver doesn't care which loss comes afterwards. But the way the supervision is given is really you're given this permutation between the key points. So there is some implicit graph kind of already given to you. And I will show the results, and the results look nice, but it is also true that we had contributions on the architectural side as well. It was helpful to have the right type of graph neural network sitting in the middle before the solver to pass around the geometric information. And we did little tweaks here and there, so we ended up beating the other methods by quite a margin. But it is not that having the combinatorial solver is responsible for all of it. This is for sure, but in fact, this points over having some naive solver in there. But what I think was the critical part was that we could focus on the right thing, because the previous methods were really trying to design architectures that dealt with the combinatorics. And we could say, no, all we need to do is build good instances because the combinatorial part is handled by the solver. So I think this was the main reason ideologically why we were able to get good performance, because we knew what we wanted and we didn't need to deal with the combinatorics. We had an expert solver sitting in the network.
We go to the previous slide. So the input is not the set of points, but it's the graph. So someone, and this is manual, has to choose which edges go into the cross function and which do not.
That is.
You can go for a complete graph in this
yes.
one, but so the manual thing is okay. Here this is from some categories bicycle. Someone chose the points. That's not automatic. Someone chose which edges will be in there. The first, what you are doing, you are saying, okay, I can get some global features and some local features so that the GM solver comes to a solution which is close to the ground.
Correct.
And it's sort of, it's not clear from here, this is symmetric, so it's sort of like Siamese. So what will be extracted from the two images will be exactly the same thing. Like,
yeah,
I can imagine it's asymmetric, so the two networks might not be the same, but here they are.
Yeah, so it's both, if you flip the two images, you get the same output.
Exactly.
Yes,
okay, so it's like, so we are saying, okay, extract edge-based and vertex-based and global information so that the result of the matching
yes.
GM solver is the correct permutation.
That is correct, yes. And so how the graph is constructed is something that we inherited from previous methods, and the default was to use a Delaunay triangulation for both graphs on both sets of points.
And we don't like that because we know that's only similarity, covariant or invariant. So if you had some sort of like a fine information, the Delaunay will change, but okay, that's fine. By
No, but it's only
why can't use a complete graph in this case?
you can. I mean, it's.
And you did try.
I think we did try it, and it just was taking longer to train, and we did not.
Because one would imagine, okay,
Yeah.
you use a complete graph and the weights on those edges which are successful come to close to zero, and you are fine, and you have selected a subset of everything possible, so you are doing the right thing.
I think the high-level reason why the triangulation was enough, other than that it's smaller and faster, is that there is this additional graph neural network that passes around the geometric information. So you have roughly reasonable types of edges, but then you have this layer that really helps you to, and this was in fact a big improvement that really helps to communicate. Maybe there's some affine transformation, you look at pairwise differences or some good geometric features that may not be embedded or maybe a little bit lost in the triangulation by itself, because still the point locations are processed inside the architecture. They are not lost. It's not that we take the triangulation and from that point on it's just an abstract graph. There is a layer which still works with the coordinates. And that was important, that was critical actually. And yeah, in the end, this worked nice. And ever since we looked at some other, ever since this was even earlier, we tried to apply this in some other settings. One of them, and I will not talk about it too much, was related to ranking. And personally, I thought that this was the least interesting of our applications because ranking is not so much of a combinatorial problem. But a lot of people cared, and we ended up providing a very simple implementation because Blackbox solver for ranking is simply torch.arcsort, which was something that previous methods were not using, and they had some explicit bits of code that were maybe a little bit complicated to suggest good gradient for the ranking. And but yeah, I think these benchmarks are even problematic, so we were a bit surprised that it was very well received. But and we have some ongoing work. About more computer vision problems that have this combinatorial flavor. Prime example is multi-object tracking. There is this need for global consistency, and that's a hard combinatorial problem, which is anyway usually solved as a post-processing step. And we might be able to solve some reasonably big chunks of it during training, and that might be helpful. But these pipelines are big, and they take a long time to understand and train, and all of that very competitive. So we'll see how we'll do. And I have 2 more videos here. We are also playing with reinforcement learning. We are trying to have this policy that jointly extracts the visual features and does some planning. So we are using a version of the Dijkstra's algorithm, which is where the edge codes are time dependent. And what we will see in the first video is the agent is trying to collect the diamond. If you know the Crash Jewel Hunt game, anyone is based on that. And the boxes will be moving in quite dramatic way. And the idea is to almost in a zero-shot fashion, after you saw maybe 50 of these levels, just to plan the whole trajectory until the end, because you have an architecture that is in principle capable of doing that. And yeah, you can see that the agent manages on this example. And we have a related project going on for autonomous driving, where again, you see that if you have this time-dependent planner inside your architecture, then maybe you can solve some interesting problems that are otherwise hard for networks. And yeah, we are getting to the end. So yes, these things are possible. Having these bits of optimized C++ code or whatever is your favorite implementation inside neural networks is absolutely possible. It's not painful to implement it, and I think modest statement is that it's competitive. You're getting reasonable performance very quickly, sometimes even very good performance. What I enjoy is this also is motivation, and we are in touch with people from combinatorial optimization who are now motivated. Hey, I've been writing these better and better solvers and nobody ever cared. And I'm saying, oh, I care, because if your solver is twice as fast, that means that I can train the network twice as fast, and I have a very good solver in it. So we are in touch, and they are excited that their progress can translate into progress on machine learning benchmarks. And one thing that I would really like to see happen is to convince the community that there is no benefit in having a differentiable solver. You still see every vision conference, so many titles. We have a differentiable solver for this, differentiable solver for that. Do what you want to do, but I would like to see this replaced by, hey, we have a better solver, faster solver. And it can be made differentiable, and that's not a step that we need to be doing explicitly. And this is something I would over time like to see happen. And these are my lovely collaborators, and that's all I have. Thank you.
So I think the gist of the message is, okay, problems with these functions, and all this can be solved by linear interpolation.
So the interpolation is actually never computed explicitly. That's an interesting point. It's interpretation of the update rule. In fact, the update rule does not construct an interpolation. It's a very simple formula. But what it does under the hood, the best interpretation of it is that it gives the gradient of some of these linear interpolations.
Okay. Now what happens goes to the maximum? So or minimum. So you get some sort of like some subgradient, or what is happening at the point of the, because I cannot imagine, so you say linear, so there must be some sort of like a rooftop situation. Probably also to be surprising if you had a unique maximum. There will be something like a rooftop where it'll have some subspace of, is that correct?
This is a good question, and this is something that we do not discuss too much in the paper, but we have some even theoretical insights that are unpublished at this point. And there is some choice inside the update rule that we already made explicitly, some choice of signs, and this choice depends on whether you want to be doing minimization or maximization. And we chose the minimization version, and in that case, what is happening with the global minimum is that as you are increasing lambda, in fact, the global minimum is reserved and everything is starting to get connected to it. And for very large lambda, the function even becomes convex. And this is a dangerous statement to make because it's a stochastic optimization problem. Nobody cares for the global minimum. In principle, it can be in a very wrong direction for the overall problem if it's the global minimum on a batch. But what we see happening is that the flat part that corresponds to the global minimum is something that gets preserved. In another way to say this is that these piecewise constant values, they start disappearing from the top and the bottom ones survive longer. So for example, we would not see this V-shaped this V-shaped situation. We would not introduce any new local minima actually.
No, but I didn't talk about introducing minima, so you have to flat plane. I would expect it to end up in some intersection of
yes.
and intersection, I would expect some dimensional subspace.
I see. So this is absolutely true. We are still differentiable in a strict mathematical sense, only almost everywhere, and we just do what everybody does, right? In terms of the community is used to having all these ReLU functions and so on that have these points only of sub-differentiability. So we make an arbitrary decision which gradient is used, and it works okay. But yeah, this is in principle problem.
So what is the magic thing in this stuff? So we have this piecewise constant function. So you say that the way to approximate it, or is this linear approximations, and it has this magic property. That's like, is this the final say in how to deal with piecewise constant functions, or
if they come from this minimizing the linear objective? But there is this one slide that I can show again. That's this one. This shows a little bit. It takes a while to explain, but it's good. It shows a little bit how this piecewise linear function, how it arises. What is it? So, originally we have only these piecewise constant blobs, and eventually there are these linear parts. And what we say is that each linear part is in fact a connector between some original two piecewise constant blobs. Not exactly. What happens is that as we solve the modified instance, the piecewise constant loss landscape for the modified instance actually gets shifted. The modification corresponds to a translation of the loss landscape. So what all these linear parts are what is called G, the orange thing on the slide. It's a connector, it's a hyperplane connecting the original piecewise constant blob with some of the original blobs shifted. And the shift depends on lambda. If you have a zero shift, then you would have this vertical hyperplane. Well, that's not great. But as lambda increases, this one stays and this one gets shifted. And the part that's appearing is this hyperplane. And each of these linear parts in the loss landscape can be traced to this process.
I have a related question. So I'm surprised you are saying that the lambda is not so important, it works for all lambda, because as if you are increasing the lambda from 0, then well, then nothing will happen for the beginning, and then it will jump and jump and jump. So if you use the lambda too high, then it will skip your local minimum. So should we use some kind of line search for the right lambda? How is it possible that it works for any lambda?
So it is, first of all, true that, I mean, I don't want to say that it works for any lambda. For example, if the lambda is too small, then your gradient is just mostly 0 and it's not good. So that's certainly true that it needs to be large enough. And then it depends on the problem. In fact, for some particular functions, even the version of lambda equals infinity has some reasonable interpretation. So there is this scalar factor 1 over lambda, which makes the gradient very small, but if you have an optimizer that is scale invariant, like Adam, this gets factored out. And even the case lambda infinity, in some cases, is a healthy update route. In fact, that is a bit surprising, but it turns out to be the case. So on some problems, the range of working lambdas is, whatever gives you enough non-zero gradient. On some other problems, like the ranking problems or the matching problems, there is a range of lambdas that work. My interpretation why a lot of the lambdas work is a bit disappointing. Deep learning is oftentimes, I don't know if you have that experience, but I feel that it's oftentimes kind of forgiving to errors in the gradient. People have tried adding noise to gradient and it even helps maybe or something like that. So as long as you're doing roughly a reasonable thing, which happens for large lambdas, you're still going to get good empirical results most of the time. So I don't want to say that it works because the method is great. Sometimes it works because the method is just good enough and deep learning can survive a lot.
So a question, so what is the overall message? So if you forget about the deep learning part, you say, in some sense, you are saying that these combinatorial problems with a linear cost function are sort of easy.
Yeah.
But what is the actual statement? Like, there exists a lambda for which I am sure to get the global minimum? Or
No. So again,
so if we get rid of, I understand that if we put this deep network before and after, it's going for some global minimum. We need to be able to find the combinatorial part, and that works fine because the deep network who knows what you want. These noisy gradients, maybe I'm avoiding local minima, and I'm doing some sort of linear, who knows what. So it works nicely, and this is sort of, it seems that the main message is that this method of approximating the discontinuous function is nicely merges what the deepness gives us. But let's say if we forgot about the deep part, and we say, is this approximation useful outside of the deep world? Is this something, say, it's like some sort of barrier method?
Well, in fact, this is very close. If we are not in the deep learning setup, if I just take the loss landscape and do some fixed modification of it, maybe I think even for lambda equals 1, I may get the differentiable upper bound that you would get for structured SVMs. So this is, for example, a connection. And so we did not use it outside of the deep learning setup. And again, the language that we use for the deep learning, our job is not to find any global minimum. Our job is to deal with the gradient. We get incoming gradient information, and we need to return reasonable outgoing gradient information. So the gradient really is the central object, which is why we focus on, every time we return a gradient, it's a gradient of one of these orange interpolators. And that's good. That's a reasonable gradient for each of these interpolators. So that's why we center the theory around that. And we are actually not fully satisfied with the theory. We would like to have something, maybe some more global statements, but we would also like them to make sense. I'm not saying we are done forever on the theory side, and there are some parts that we would like to do a bit better.
I think I'm getting to say this is the best way to approach something like that. You're saying, okay, when we're between two flat surfaces, will be guiding you
Yes.
towards the higher one.
Yes.
If you are somehow in between, it's not clear what is in between because
Yes.
many of those things. But pointing to some, and no matter where you are, will send you towards the higher level.
Lower for the minimization, but yes, this is the idea.
And this, in the context of SGD, where also random things are happening, this is good enough. And in the end, the proof is in the results, which show that when we connect it with a real deep nets, it looks better than not putting it at all and asking the network to somehow magically figure out which permutation.
Yeah, I think that's a fairly accurate description of the message. Yes.
What is the problem when I set the lambda too high? What can happen very fast?
I mean, in practice,
Yes.
the loss will not go down. So the loss function will not go down. That's what will happen, because on the forward pass you run the exact solver, right? So the only thing you want from this proposed gradient is that you are minimizing the loss function, because the loss function only depends on the forward pass. So if you are returning gradient, that makes very little sense. You will just not be minimizing the loss function. So this is what will happen, that you will get stuck in some sort of loss values that you can clearly beat if you have a better value of lambda. Am I answering your question?
Possibly.
And one more question, which relates to I guess that how do you set the lambda on the percentage of backward passes that did not lead to any updated weights? Because if the lambda is small, I guess you will get often a zero gradient, and that's an indicator that something is wrong. So maybe you can say, well, okay, you have the guarantee for lambda 0, so you can say, give me, and you can do this dynamically. I keep my lambda, like, okay, so if we have also zeros, fine, maybe I'm not modifying my function, but I'm very grossly inefficient. So let's keep the lambda the smallest that will have, I don't know, 80% of non-zero gradients. And that now sounds quite nice that I'm trading a little bit of efficiency for the approximation. And if I'm doing 80%, I'm fine. And I'm keeping it closer to the guaranteed setup.
Yeah, that's exactly what we tried and did, and we are still waiting to come across problems where this actually makes a difference. That's a little bit frustrating because exactly we would like to see that, hey, if we do this, it's going to be a little bit better. But if you don't do it, have a reasonably tuned constant lambda, yeah, you minimize the loss, and that's hard to beat. So I would love to see that. It's almost frustrating, really. I think this is exactly something like that should happen, that you would, have some smart way of choosing the lambda, but we are waiting for a use case when we will really need it.
Okay, so your result is no matter what lambda we use the result. So I
think I would say that
benchmarks you want to have the best numbers. That's always nice, people. So you try for a couple, and the difference is 80% 1 to 80% 1.5 or something like that.
Yeah.
Almost.
So that, usually there is like an order of magnitude gap where the lambdas work just as well, and there is deterioration on either side. So you don't need 1.75. You just say it's 20 and 40 still works and 10 still works. It's not that each constant works, but yeah, there's like a gap that's usually an order of magnitude.
In the matching problem with images, how many points were there in this maximum number of points?
I think the maximum number of key points was around 20, and the median was around 10, 8. So the instances are actually quite small. And again, for this smaller instances, we did not feel the solver in the runtime because the solver was very fast. But it is an NP-hard problem, and you want to solve it many times in a single batch, right? For each pair of images, you want to solve it. If we had about 40, 50 key points, it would still be doable, but the bottleneck, the solver will become the bottleneck in terms of runtime. So this is also, I don't want to make it sound like, we can handle everything with the method. The method is only as good as the solver you can use. So if you have really large instances, then yeah, the solver there might not be a good solver out there that can solve it in a fast enough runtime so that you can solve it every time on every iteration of the deep network training. So actually, we really choose our victims carefully. The problems we apply this to, they needed to be chosen carefully. It's not that you can just say, oh, this feels like combinatorial ban, and the instances have thousands of vertices. And yes, so this is a limitation by all means.
And in this experiment, does the solver always find the optimum solution? Or do you find the optimum?
So in the ICLR paper, we have the exact solvers, and we always got the optimal solution. The solvers for NP-hard problems depends. Sometimes they come with guarantees that they stop only at the optimum, sometimes not. And yes, so we do not have any guarantees ourselves. What happens if the solver gives suboptimal solutions, but in practice it works all right? We even had a case that was exciting. If you have a suboptimal solver for the traveling salesman, then your test case performance already has a ceiling, because the solver, even if you give it the correct instances, not the learned instances, but the correct instances, will only solve correctly as many. And what happened is once we trained with the solver, our test performance was a bit better than the ceiling. That the deep network adapted to the bugs in the solver a little bit by 1 or 2%. So it learned to feed a slightly wrong instance so that it gets the correct outcome. That was quite interesting. And empirical. We don't know theoretically what happens, because who knows what happens if you get wrong solutions from the solver. But so far we had good experience with it.
So if I'm not wrong, you mentioned that the combinatorial solver essentially appears towards the end of the model. How does the initialization of the rest of the model is affecting the optimization? Is it like you're initializing with a pre-trained model with some different loss function somehow, or is there an initialization?
We did not need to modify the initializations compared to how they are done by default. I mean, there's a little bit of consideration. In principle, there might be some subtle considerations. For example, if your initialization is unfortunate, that what goes into the solver on initialization is all numbers being equal, because somehow they got all equal to 0, then you're in the region where if you make an epsilon change to anything, all the combinatorial solutions are in your neighborhood, so your gradients are a little bit crazy. So as long as your initialization is well behaved in deep learning sense, is well behaved enough for the solver.
Just wondering, you were saying that there are these new differential solvers proposed, but this is sort of a black box optimization, so I don't really care what's in there. So have you tried an experiment where you would use this differentiable solver, but you would not use the gradient from this thing? How does this compare?
Right. So we have some experiments. So we did not do this experiment in the synthetic setup, and we did it in the matching case. There is a differentiable matching solver that we used, and we lost a bit of performance. I don't even want to say necessarily that we are winning on performance. We should be winning on performance when the combinatorial part is hard, when you have to pay for the combinatorial sacrifice, which might be happening a little bit on the matching problems, because some of the instances are really nasty if you have the sheet turned around and so on. And we actually had some table in the paper where the instances are ranked by difficulty, and we could see we have the biggest gain on the hardest examples. That was satisfying. So something like that needs to happen. But otherwise, yeah, our main point is if the combinatorics is hard, and you don't have to have specific differential solvers. So in some small experiments we saw, I would even say that if the combinatorics is easy enough, it's going to give us 8. I would not gladly. You will get a difference once it pays off to have a better solver. And this, many times the bottleneck is really in something else. The bottleneck. We still know that next time new ResNet comes out, we'll get 0.8 on detection benchmarks. And so probably this is not the bottleneck, maybe not the matching procedure inside, and so on. But in some problems, the combinatorics may be the bottleneck, and this is where we would like to be applicable.
Yeah, true. But you can always use this black box for things.
Michal again.